Good day, everyone. In today's lesson, we'll be looking at one interesting topic and very fundamental in physics called equilibrium of forces. At the end of this lesson, we'll be able to know what an equilibrium or what an equilibrium is, okay, and then what equilibrium of force really is. We also know some of the physical quantities in this concept, such as moment of force and couple, and a little calculation question involved. So let's dive into this topic. Now, first of all, let's consider the first physical quantity that you must know in this topic, and that is known as moment. Before we dive into principle of moment, we need to know what moment itself is. Moment, how do we define moment? Before we define moment, let's do a little analysis of this diagram you could see here. This is a balance weight, okay? In this balance weight, you could see that there are two objects, object to be weighed, okay? One on the left and one on the right. Now, let us assume that the one on our right hand side is much more heavier. Let's call it maybe 60 gram, and the one on the left is 20 gram. Now, by the time you hang them this way, what you expect to see is that the one of 60 gram will drag this way downward, okay, to go downward, and the turning point will occur here, right? So it will take this downward, and then this 20 gram will go up because it's lighter. Now this is called this turning point, okay? This is a turning point. Now, there's also something again we need to consider: the distance of the weight from that turning point. For that of 60 gram, let's say it is y centimeter, and for that of 20 gram, let's say it is x centimeter. Now, moment by formula says that it's going to be the product of the force, that's the weight here, that's what we call it. I'm calling force now. The product of the force and the distance of that force from that turning point. Okay, so for that of 60 gram, its own moment for 60 gram moment is going to be that 60 times a distance from that turning point, which is y. Then for the 20 gram moment, it's going to be 20 gram moment will be giving us 20 times x. So what then is moment of a force? Moment of a force simply is defined as the product of force and the perpendicular distance. Why do we say perpendicular distance? It must be a distance from that turning point. The distance must be at 90 degrees. Perpendicular means 90 degrees. So the distance between that object and the turning point must be at 90 degrees to each other. That's why we say moment is the product of the force and the perpendicular distance of the force from the line of action of the force. Okay, that's the definition of moment. Then let's now go to principle of moment. Principle of moment now states that in an equilibrium, when we say an object is an equilibrium, that means the object is not turning, neither is it moving forward or backward. So if you don't want this object that is turning here now to turn either upward or downward because of this weight, we want it to remain at this horizontal position, then principle of moment say that the moment of 60 gram must be equal to the moment of the 20 gram object. So it's saying that clockwise moment, this one is going upward, that's clockwise, while this one is going downward. So it's saying that clockwise moment must be equal to what? Anti-clockwise moment. That's what the principle of moment is stating. That for a body to be at equilibrium, the clockwise moment must be equal to the anti-clockwise moment. I hope that is clear. Now, we've talked about the moment of force now in the previous slide, the product of force and perpendicular distance. So meaning that either the formula, we use this symbol to represent moment of force, this T-shaped kind of symbol, okay? If we want to represent a moment of force. Sometimes we also call it torque. Another word for moment of force is called what? Torque, T-O-R-Q-U-E, all right? Now, moment of force is product of force and a particular distance. Now, because of this formula, the unit will now be Newton meter, because force is in Newton and distance is in meter. So the unit of unit of torque or moment of force is Newton meter. That is the standard SI unit of torque or moment of force. Okay, now another concept or physical quantity under equilibrium of force is called couple. Couple also has the formula for had the same formula with the moment of force times distance. But by definition, they are not the same. A couple is a system of force where you have two equal forces, but they're in opposite direction. Okay, acting at different points along the same line. And a good example is the steering wheel of a car. Look at this now. The steering wheel of a car is a good example of a couple because the driver will apply the force of the right hand side and the force of the left hand side. Okay, these forces are the same thing. If it's applying 10 Newton on the right, it's also applying 10 Newton on the left. But what happens is that as it's turning with the right hand upward, then the left hand will be taking it downward. So they're in opposite direction. That's why we call it couple. So a couple is a system where two forces of equal magnitude act in opposite direction to rotate an object. The objective is to rotate that object. Like I said before, it had the same formula with moment of force times distance. An example is what? Your steering wheel. Another example is your water tap. When you are turning your water tap, and even when you're making your corkscrew to open your wine, you are making use of a couple system. Okay? Now, we now talk about another part in this equilibrium forces. There are two major forces that occur in equilibrium of force. We have the equilibrant force and we have the resultant force. Okay, let us analyze that quickly. When we say equilibrium force and resultant force, this is what we mean. Imagine this object, okay, being acted upon by two forces. Let's say force F1 and force F2, right? Now, this force F1 and force F2, they're acting in the same direction. What will happen to the object? The object will move in their direction, is it not? Okay. Now, the total force will now be F1 plus F2. This total force is what we call the resultant force, Fr. So, a resultant force is a single force that represents the combined effect of multiple forces. But then, if you don't want this object to move, then there must be another force that must move the opposite direction. Let's call that force F3. Now, this force F3 will not allow these two forces to move this object forward. Now, for the fact that this object cannot move forward again because of this F3 is called the equilibrant force. Okay? Equilibrium force. So, equilibrium force is that single force that counter the other forces. Okay, because it's all moving in the opposite direction. So we can say that equilibrium force is the same thing as resultant force, but it acts in opposite direction. So as you can see here, FEQ is equal to minus FRA. That is, resultant equilibrium force is equal to minus resultant force. So they are equal forces, just like couple, but they act in opposite direction. Okay, so that is the forces that act in equilibrium of forces that we need to know: the equilibrium force and the resultant force. So having said that, let's now talk about the conditions that will make an object to be at equilibrium. Remember, we've said that for an object to be an equilibrium, that object must not rotate, neither should it translate. In other words, move forward or backward or move on a straight line. So for this object not to rotate or translate, then two conditions must be obeyed. Number one, the total force that is acting on that object must be zero. And then the total moment of force also on that object must also be zero. So the net force must be zero and the net torque, which is also moment of force, must be zero. These are the two conditions that must be met for an object to be at equilibrium. So we also have another concept again that is called center of gravity. The center of gravity is the point where the entire weight of an object seems to act. So every object has a point in them where all their weight act on. And how can you find the center of gravity? By experiment. First of all, just hang that object Okay, after hanging that object, then get a plumb line and hang it beside that object, and then trace that line. Okay, note that line of the plumb line. Now locate another point on that object with your plumb line, and also note the line. So where the first line and second line intersect, that intersection intersection point is referred to as the center of gravity of that object. Okay, now this leads us to what we call types of equilibrium. Equilibrium is linked with center of gravity in this manner. Now there are three types of equilibrium. We have the stable equilibrium. When we say an object is stable, okay, when we say the equilibrium of an object is stable, it means that when you tilt that object or you displace that object, the object will quickly return to its original position. Look at this object now. If you tilt it forward now, what happens? It will go back because it is at a stable equilibrium. When an object is at stable equilibrium, the center of gravity is at the lowest state. When the center of gravity of an object is at the lowest state, it is very difficult for that equilibrium to be altered. On the other hand, unstable equilibrium is the case whereby if you tilt that object, look at this object now, this object is at this unstable equilibrium. But if you tilt it, what happens? It will fall. It will move away from its original position. So when an object moves away from the original position, then you say that that object is at its unstable equilibrium. And in this case, the center of gravity of that object is at the highest possible point. So stable equilibrium and unstable equilibrium, they are opposite. For stable, the CG is at lowest possible point, while for unstable, the CG is at the highest possible point. Then there is this neutral equilibrium where the object just remains in its new position after you have displaced it. Unstable equilibrium lead to neutral because if you tilt this cone now, what happens? It will lie on the ground. And as it lie on the ground, it's already now at its neutral equilibrium. It can no longer, change its position anymore. So in this case, we can say that the center of gravity is at its geometric center. So it is in neutral equilibrium that you have the center of gravity of an object to be at the geometric center. So having said all of this, let us consider some questions to give us better idea of what we are saying. Okay, now look at this question here. It said, which of the following statements are correct about an object in equilibrium under parallel forces? Okay, remember we have talked about these conditions. Number one, I said the total clockwise moment of the force about any point equal the total anti-clockwise moment about the same point. That is true. The same thing as saying that moment around about that point must be zero. The total moment must be zero. It's either you say they must be zero, or you say that the clockwise moment must be equal to what? Anti-clockwise moment. So this I is correct. I. The total forces in one direction equal the total forces in the opposite direction. It's also true. This is another way of saying that the total forces acting must be zero. So it's either you say that the total force acting must be zero, or you say the total force in one direction must be equal to the total force in the opposite direction. It's the same thing. It's just like the first one. And third one said the result component along the x-axis equal the result component along the y-axis. That is not true. They cannot be equal. Okay, so the only correct ones are I and I, and that is A. A says I and I. B says I and I. That's not correct. C says I and I. That's not correct. And D say I and I. No. The only two conditions that we need is that the total moment must be zero, or you can put it like the clockwise moment must be equal to anti-clockwise moment. And the second one is the total force must be zero, or you can say that the forces in one direction must be equal to the forces in the opposite direction. So the correct option is A. Right? Let us see another question again. Here we are told that a uniform beam PQ of mass 20 kilogram and length 5 meters is balanced as shown in figure 8. This is figure 8 here. Okay. A man of weight 800 Newton stand at M. Okay. Such that QM equals to 2 meters. I could say, yeah, this is where the man stood. Okay, so the reaction at P and Q respectively are what? We have to take G to be equal to 10 meter per second square. Okay, so this question is very straightforward. So we are going to take it one after the other. First of all, we are told, pay attention to that word, uniform beam. When something is uniform, okay, it means that the center of gravity of that object is at the middle of that object. Okay, so if this uniform beam, for example, is 50 in length, 50 centimeter in length, it means that the center of gravity is at what? 25 centimeter. So take note of this word uniform. Whenever you are told uniform, it means that the center of gravity is at the center of that object. So let us draw this uniform beam PQ again for clarity. Okay. Now let's quickly have a sketch of this so that it will be clearer to us. So this is a diagram. Let's make it a little longer. Okay. So this is a diagram, a beam PQ. So let's put P here. A beam PQ, let's say P and Q, okay, of mass 20 kilogram. Now, because the beam has a mass 20 kilogram, okay, that means the weight is acting at the center. This 20 k is acting at the center. And length, the length of this beam is 5 meters. So that means from P to Q by length is 5 meters. Okay, it means that the weight 20 kilogram is acting at the center. This 20 kilogram, yeah. So it means the weight is acting at the center, which is 2.5. Half of 5 is 2.5, which is 2.5. Because it is uniform, take note of that. So the weight is acting at the center. Okay. Now, a man of weight 800 Newton, a man of weight 800 Newton stand at M, so that QM is 2 meters. So from here, the man is standing between Q and M here. The man is standing here and has a weight of 800 Newton. That's 800 Newton. Now this one is 20 kilograms. To convert mass to weight, just multiply it by the 10 given to us here, so that this 20 by weight will now give us 200 Newton. Just 20 times 10. Okay. Now remember that we are told that the man stand at 2 meters from Q. The man is at point M here, but between here and here is 2 meters. Okay, and then definitely what is now remaining here, because this is 2.5 here, so what is remaining here would be 0.5 meters. Okay, that was remaining there, because from here to here is 2. Definitely from 2.5, 2.5 minus 2 will give us 0.5. Okay, so we are going forward. So now the reaction at P and Q. Reaction means the force that is acting in the opposite direction. The actions are the weight of the object down, the weight of the man down. Now the beam will also react because they are sitting down on it, so the force will be acting upward. Okay, so this point here is reaction. Reaction at P is upward. Reaction at Q is also upward. As you could see in the diagram, you can see that the forces are acting upward. So what are the reactions at P and Q respectively? Okay, very simple now. Now, where is the turning point? That's where you should take note of. And the 2 points P and Q are turning points, but they cannot turn at the same time. It's either this beam turns at Q or it turns at P. Okay. Now, if this beam turns at, if it turns at, let's assume that it's turning at Q, it means that it will be moment of this 800 Newton times the distance. Remember, moment is force times distance. Let's do moment about this point Q for 800 Newton. So it will be 800, that force, that will be 800 times, remember that this is the distance from there to the point, times 2. Okay? So then plus the moment of the second one, 200, this 200 Newton from that turning point P, plus from here to this place is 2.5. So it's going to be 200 times 2.5. Okay, that is the total clockwise moment that is acting here. Okay, but there is no anti-clockwise moment. So going about this method might get us stranded. How do we get the anti-clockwise moment? There is no point where this is going to turn. This is turning from here to this place, and it's also turning from here to this. So how do we not get the anti-clockwise moment? You can now look at this P here. The P is the one that is going in the clockwise direction. Okay, this force is going down, the P is going up. Okay, now the perpendicular distance from P will now be equal to 5. You know, from P down to this Q is 5. So it's going to be P times 5. All right, so this one is 800 times 2, which is 1600, then plus 200. So our 200 times 2.5. Okay, so when you multiply 200 by 2.5, so that should be giving us 500. Okay, so here we have 500 to be equal to, on the other hand, you have P times 5, which is going to be 5P. You understand? So 1600 plus 500, that will be giving us 2100, which is equal to 5P. Dividing both by 5, P there will be 2100 over 5. All right. Now when you do 2100 divided by 5, you should be having 420. So here our P here is 420 Newton. But remember, we have to get P and Q. How do we not get our P? We apply the first equilibrium condition, which is the total force that is acting in one direction to be equal to total force in the opposite direction. So the upward forces are P and Q. So it's going to be P plus Q must be equal to the total force acting in the opposite direction, which are 200 and 800. It will be 200 plus 800. Remember that we have gotten our P to be 420. So we can say 420 now plus Q equal to 200 plus 800 is 1000. Now Q there will now be 1000 minus 420. Okay. So if you subtract 1000, from 420, that will be giving us 580. So our result will be what? 580. Okay, so we have it to be equal to 580 Newton. All right, so we have 420 and 580. Okay, so P, now take note of this, at P and Q respectively. So in our own case, P is 420 and Q is 580. So the option is option B. All right. So We'll be joining the curtain here today. I hope you're able to understand how the principle of movement works under equilibrium of forces. Thank you for listening and have a wonderful day. Bye for now.